Hey everyone, Mr. Fransky here. Hope you're having a great day. We're going to jump into chapter 4 today, which is applications of derivatives. We're going to take this idea of the slope of a tangent line, which we've just been finding over and over again, and actually applying it to some interesting problems. So in 4.1, we're going to talk about extreme values. Extreme! So extreme! And students will be able to find extreme values of a function where they occur using calculus. So let's take a look. Oh, it's so extreme! All right, so we're going to talk about derivatives, maximum, minimum, and critical points in this video. So extreme value theorem. So extreme. So the extreme value theorem says is that if f of x is continuous on closed interval AB, so that means it's including the endpoints, then f of x has a max and a min on closed AB. Now this makes a lot of sense to me, right? If you have A over here and B over here, and A to B, you are continuous the whole time. Let's say something like that. Okay? Then there is a maximum value. It looks like in this case, it's whatever f of A is. That would be my maximum value. My minimum value is whatever the heck this is over here, right? So it has a maximum and it has a minimum. If you're continuous, this always has to be true, even if it's not differentiable, right? So anything that's continuous on a closed interval is going to have a maximum point and a minimum point. Okay, so not too bad. Extreme value theorem is not something that really comes up a whole lot. It's just something that's interesting to know. Now, one thing that AP does a lot is they talk about functions being differentiable, but they don't mention continuity. So they'll say like f of x is differentiable on like 3, 7. They might say something like that. Now this is important. Differentiability implies continuity. If they tell you it's differentiable, it's guaranteed to be continuous. Why is that? Because in order to be differentiable, it has to be continuous, right? Like we talked about this before. If you have a function that's not continuous, like if you have an asymptote, it's not going to be differentiable on the entire way through that point. But if you're differentiable, if you have a smooth curve, like at this point, definitely differentiable, right? Any point here, you could find a tangent line. Then it brings up this question of, anytime you're differentiable, it's for sure going to have to be continuous. Yeah, cool. So differentiability and continuity. So this is what AP usually does, is they say f of x is differentiable on this interval, and then you have to use the fact that it's continuous to talk about extreme values and whatnot. Nice. Okay. So the converse is not necessarily true. It is possible to be continuous but not differentiable, right? Like if you had a corner. Continuous but not differentiable. Okay, so just be careful when you're talking about whether things are continuous or differentiable. They're not interchangeable. You have to make sure that differentiability is the stronger case, because that means that it also has tangent lines everywhere. All right. So find the maximum minimum value of f of x equals x squared on the interval -1, 2. Where do they occur? Well, let's graph it. Here's -1. When I plug that in, I get 1. This is just x squared, so it's going to come down, and it's going to turn back up. And then at 2, we're at 4. So something like that. So it looks like our max value is going to be 4. And that happens at x equals 2. So this is important, right? Things happen at x coordinates, and they are y coordinates, right? So the y coordinate is the actual maximum value, and the x equals 2 is like your roadmap to tell you where it happens. Our minimum, looks like our minimum happens, it is 0, and it happens at x equals 0. There we go. Cool. Not bad. All right, relative versus absolute min and max. Let's say you have something that looks like this. Yeah. Okay, let's say this is on an axis. Let's say this is -1. Let's say this is like 5. Say this is 3, and this is -1. And this is 4, and this is 3, and this is, let's say, like -4, and this is, let's say, -5, something like that. Okay, so we have some points here that are relative minimums and maximums, and we have some that are absolutes. So relatives just mean if you zoomed in on that part, it would look like the top or bottom of the world. Okay, so there are 1, 2, 3, 4 different spots on this graph that are relative maximum or minimum, and some happen to be absolutes as well. So my relative list here. So these are relative maxima or minima. So negative 5, x equals negative 5, gives a relative minimum of what? Of negative 4. So negative 4 is the y value. That's the actual minimum value, and it happens at x equals negative 5. The x-axis is like your roadmap. It tells you where to go to find out certain things. So x equals negative 1 in this case is a relative maximum. And it happens to be 5. X equals 3. X equals 3 is a relative minimum. And that happens at y equals negative 1. And x equals 4 is a relative maximum of 3. Yeah. Okay, now some of these are absolutes, right? The negative 4, that is an absolute. Oh, where is my negative 5? There it is. What do I want? Here we go. That's an absolute, because there's nothing lower on the entire interval. And then the other one would be at negative 1 for x. Yeah, this one. Okay, so those two are kind of the special ones because they are also absolute maximums and minimums. Nice. Okay, so how about something like this? Let's say this is negative 2, negative 3. Let's say this is 4, 2. Well, let's make it 4, 5. It doesn't really matter. Okay, but a lot of people see this and they say, oh, the maximum value is 5. Well, not really, because there's an open circle there. Think about it. You could get as close as you want. If you tell me like 4.999, I'm going to say, okay, but 4.9999999 is even higher than that. So I can get as close to 5 as I want, but I can never touch it. So this has no max or min values. Okay, and the important thing is that's why the brackets are important on our continuity premise, is that you have to have it continuous all the way through from A to B. Cool. All right, critical points. So I'm going to draw something here. Let's say like that. So what I want you to think about is, where do the maximums and minimums occur? Hopefully you see there's a max here, there's a minimum here, there's a max here, there's a minimum here, right? So let's think about where those things happen. What's going on with the calculus at those points? So at this point, it's not differentiable. At this point, it's differentiable, but the slope is 0. Same deal here, and this guy is not differentiable. So it looks like there's some kind of tie between things that are maximums, minimums, and things that are corners or not differentiable points. So here is what this little kind of, I can call it a theorem, I guess, says. So what they say is that the so first let's define critical point. So a critical point is where the derivative equals 0 or it's undefined. Let's see what happens here. Here's an undefined. Here's a 0. Here's a 0. Here's an undefined. And that's exactly where all the maxes and mins happen. So this is what the theorem says. The maxes and mins happen only at critical points. There we go. Okay, so maximum and minimum happens only at critical points. So what that means is, if I want to know where maximums and minimums happen, just take the derivative, set it equal to 0 or find when it's undefined. And then you're going to test each one to see if it's a maximum or minimum. So the reason we do that is because we could have some absolute maxes, some absolute mins, and if you only get like a maximum value and you don't ever get that it goes off to infinity or anything, then you have found that absolute maximum or absolute minimum. So to find maxes and mins, all you have to do is find out where the derivative is 0 or undefined. Find out where it's 0 or undefined and you're good. Okay, so one more here. So we're going to find the maximum points for f of x equals ln sine x for the interval 1/2 to 5/2. So what I'm going to do is take the derivative here. So f prime of x would be 1 over sine x times cosine x by chaining, right? So that's cotangent x. Okay. because it's cosine over sine. Now what I know is, so cotangent x, I'm going to find out when it's 0 or undefined, and then that's going to put me back into my original function, which will tell me if it's a max or a min. So what I'm going to do is think about cotangent x between 1/2 and 5/2 and see are there any zeros or anything like that. Well, 1/2, think about the unit circle. 1/2 radian is like over here somewhere. 5/2, that's 2.5, it's like over here somewhere. So cotangent is 0 right at the top of the circle. Okay, that's pi over 2. So my critical points, pi over 2, because that's where the derivative is 0. And then on that interval, I don't think cotangent is ever undefined. So what I have to do is just think about what's going on with pi over 2 in the original function. If I plug pi over 2 in there, I get natural log of sine of pi over 2. Sine of pi over 2 is, that's the top of the circle, it's 1. So this is natural log of 1. And so the question is, e to what power is 1? That's 0. Okay, so I'm going to guess that is a minimum point. But to figure it out, I would have to plug in something else nearby. So they want to actually find the point, so maximum minimum points on 1/2 5/2. So 1/2, say this is 5/2 over here. So what I'm going to do is make a list here. So I have my x points, and then I have my f of x points. So these maximums and minimums, I think I said on the last slide, they can only happen at critical points. They can also happen at endpoints. I can't believe I forgot to say that. So critical points or endpoints. I must be tired. That's because we saw it before, right? If you have a function like this, the maximum's right there. That's an endpoint. The minimum's over there. It's also an endpoint. It's not at the relative max and mins, right? Because we're looking for the absolute. So all I have to do now is plug these values into my original function. So I have 1/2, I have 0, and I have 5/2. So we just found out that we plug in 0, sorry, pi over 2, not 0. I'm jumping ahead of myself. Pi over 2. Plug in pi over 2, we get 0. Plug in 1/2, you have sine of 1/2, which would give you a positive value, and then take the natural log of it. So this is going to be a natural log of sine of 1/2. I don't even need a calculator to know that's going to be positive. Then the last one's going to be natural log of the sine of 5/2. Let's think about that. 5/2 2.5. And pi is 3.14. So we got 3.14 over here. I just want to know which one's bigger. So sine of 5/2. So every one of these gives a bigger number, so one's going to work. Sine of 1/2. 1/2 radian would be like 23-ish degrees. So it's like over here. And then what's our other one? We got 5/2. So 5/2, that's 2.5. So 2 radians is like 114. Plus another like 24, so this is like 128. Yeah, so it's like over here somewhere. That's going to be a pretty tight race. I'd grab a calculator and see which one of those is bigger. But this is definitely our min. So there's a minimum at pi over 2. And our max I think is going to be, let's say this is 128. That's, is that right? More or less 2.5 times 57, 114. Yeah, yep. So yeah, I don't know, whichever one is bigger. You have to grab a calculator to check those out, but kind of cool. So this is called the test point method. We're going to be using that a lot this year. So if you want to find maxes and mins, always nice to make a table of all the critical and endpoints, and then just see which one works out for the biggest or the smallest. Cool. All right. I think that's all I've got for this video. Yep. So I will see you on the next one. Love you guys. That's why I'm here. Have a great day.